Hello, everyone. Welcome to MACSMIN 2025. Our first talk, it's a great pleasure to introduce Professor Janos Pach from Rényi Institute and also EPFL, who will talk about mysteries about crossing numbers. Over to you, Janos, please.
Okay, thank you very much for inviting me. I think that I haven't been to Liverpool for 40 years.
Oh,
at that time, I think it wasn't the case that everything was named after John Lennon. That's a big change. Okay, so what is this thing here? Can we make it go?
Yes, sure.
I should say okay.
Click.
Hopefully, yes. All right. So this is John. And I will be talking about crossing numbers. I thought that you will see that this is a crossing and this is not a crossing. So this is just a kind of the definition screen, but I will give more of a definition. It's about graphs, but I think it's appropriate that I give this talk at an institute whose name has the factory in it, because the problem really started with the so-called brick factory problem. It will give me all kinds of messages, doesn't matter. So maybe these things, what can I do with it? Minimize it.
Minimize, yeah, and move up.
And move up.
Yeah.
Okay, the best I can do. Okay, so this is Turan's brick factory problem. This is the starting point of this talk and the whole subject of crossing numbers. And so it started in a brick factory where Turan in 1942 worked as forced labor. And the job was to fill wagons with bricks, and there were a number of kilns where the bricks are made. So I denoted them by these blue points, and there were a number of storage places. They are these red points. Their location in the plane is at the moment not important, because as you will see, at least in this setting of the problem, it's topological. You can move around the points, and even the edges of this graph are not necessarily straight lines. But the setup was that every kiln was connected to every single storage place by a pair of railroad tracks. And so they had to push the wagons filled with bricks from the kilns to the storage places. And as it turned out, it wasn't a very difficult job. The only difficulty was when two railroad tracks crossed, because there they had to push harder and many bricks fell off. And apparently the workers cursed a lot. And it occurred to Turan that one should optimize the design of the railroad tracks so that to minimize the number of crossings. And in fact, he was considering that he was in a labor camp. He was lucky because he had a military commander who actually appreciated mathematics, and he let Turan set aside some time for thinking about mathematics, and he did. He couldn't solve this problem, but the problem, the name Turan's brick factory problem, was popularized by Erdős, and shortly, 9 years after the war, Zarankiewicz published a solution to this problem, and the solution was that you get the minimum number of crossings if in this configuration, where you put half of the kilns on the x-axis to the left of 0, half of them to the right of 0, half of the storage places on the y-axis above 0, half of them below 0, and every kiln, every blue point, you connect to every red point by a straight line. And if you do the computation, actually, if there are m blue points and n red points, then you can find that this is the number of crossings. Now, shortly after Zarankiewicz's paper was published, several people found a gap in the proof. So the theorem became a conjecture, and the equality became an inequality. So this is the best we know. Everybody conjectures that this is indeed optimal. But the sad state of the matters is that, so assume that m is equal to n. Then this expression is roughly n to the 4 divided by 16. So we know that n to the 4 is the right order of magnitude, but even the constant 1 over 16 is not known. So there are many computer experiments which suggest that that at least for small values this is optimal, but we still don't know the right constant here, and this is a very challenging problem. You may ask that, okay, so this is like a complete bipartite graph. Perhaps it's more natural to ask the same question about the complete graph. When there are no red and blue vertices, just n vertices, everybody is connected to everybody. How do you draw that? And this was considered by Anthony Hill, a British artist, fairly well known, who definitely was interested in mathematics, and he came up with this drawing and suggested that this is the smallest number of crossings. And if you calculate it, then this is the number you get. But it's again unknown whether this is true. Again, even the constant is not known. But most likely it is not an easy problem, because here, although it's not obvious on the picture, but there are two essentially different drawings that give precisely the same number. It's a longer story, but generally, you know, it's to prove that something is optimal if there are a lot of different extrema is difficult, because the general strategy usually is that we try to prove that if we start from an optimal drawing, then the optimal drawing should look something like this, and then with some more work you prove that it should look exactly like this. But this is not the case. There are many extremes. It's like shadow boxing. You have no idea where the enemy is. So now we have all kinds of ways how to use computers to estimate this thing, and in particular flag algebras. And so we got close to that. So instead of 0.25, we know that the best drawing, the number of crossings should be at least 0.245, which is pretty close to the conjecture, but not the same. Also, I should mention that if you solve this, then it also implies the bipartite solution. Now, let me show this picture, which is in the Tate Gallery of Anthony Hill. So it is clear that actually all of his pictures are geometric and then very interesting. Here is the person himself, who was a heavy smoker, as all artists, I think, in the 1960s, was a heavy smoker and an alcoholic. And as a consequence, he lived longer than 90 years. And well, I don't know if this is probably just anecdotic evidence, so it doesn't show that this is what you are supposed to do if you want to live long. So anyway, obviously you can ask the same question about any graph. So you are given the graph, you want to draw it in the plane, or as a matter of fact, on any surface. I don't want to talk about this more complicated version today. So just in the plane, you want to draw it in such a way as to minimize the number of crossings. But again, this is crossing, touching is not crossing, but if there is a touching, then you can slightly remove these things. So this is the crossing number of a graph, and the crossing number is 0. It means precisely that you can draw the graph without crossing. It's a planar graph. And then the planar graphs are very well characterized. Kuratowski's theorem, we know linear time algorithms for deciding whether a graph is planar. We know everything. Now, if we move away a little bit from that, so we talk about graphs whose crossing number is at most 1. What does it mean? It means that they can be drawn so that there is just one crossing altogether. Then these graphs can have a characterization. This is a deep and difficult theorem by Robertson and Seymour. And it's a beautiful characterization in terms of 41 forbidden minors. So if you don't know the definition of a minor, it is some kind of a subgraph. You may wonder that how the hell can a theorem be beautiful if, first of all, if it contains the number 41, and then secondly, 41 forbidden configurations, because, you know, for planar graphs, they know that the K33 and the K5 are forbidden. Now, there are 41 different things. But the strange thing is that those 41 come from the so-called Robertson. They come from one graph, and they are very easy to describe. And once you understand the structure, it's really a beautiful theorem. And then you would think that, well, probably life gets more complicated if you increase this number 1 to 2. And this is indeed the case for, as far as I know, there is no characterization of graphs whose crossing number is 2. No known characterization. And it's indeed a difficult problem. This was one of the first empty complete problems on the list in the book of Gary and Johnson, which was published in the 1980s, where which was one of the starting points of complexity theory. Okay, so given that we cannot determine exactly the crossing number of a graph because it's difficult, even asymptotically for the complete graph, which is amazing, any kind of estimates and results for the crossing number of a graph are useful and important. And in fact, perhaps the best known among them is a crossing lemma, which was discovered by this group of people and Tom Layton, who was a PhD student at MIT. And there are these two names here that I mentioned because in the first version, the constant is 1 divided by 64 or something like that. So it's since then, since the 1980s, the only thing that improved was the constant, which is today 1 divided by 28, which is not tight, but probably it's not very far from being tight. So 2 remarks here. First of all, again, you may wonder what the hell this ugly expression E cubed divided by n squared is. E is the number of edges and N is the number of vertices. Well, the first remark, so first of all, this is the best you can say. I will tell you in a second. But you need to assume something, because this is a positive number. If the number of edges of the graph is 3n minus 6, then the graph may be planar, right? So then there is no crossing. There is no way how you could give a positive lower bound for the crossing number. So you have to assume it's not planar. You have to assume it's bigger than 3n. So to get a normal constant, we assume it's bigger than 4n. But if here we write bigger than 5, and then maybe we can improve the constant a little bit. Not much, not much. But to understand what it means, let me try this here. Thank you very much for providing me. I will. Okay, thanks. So maybe I move this. Not that I would hope that anyone can see it, but who knows, you know?
Yeah, it's visible.
Is it? So let's just understand what the hell it is. So assume that your graph is dense. This is one of them. So what does it mean? Okay. Maybe I was overly optimistic.
Please try one more. And
yes, okay.
I'll find.
Okay, this sounds good. So what does it mean? It means it's dense. It means that, well, a graph can have a quadratic number of edges, right? So indeed, like a positive percentage of the edges is there. So if the number of edges is constant times n squared, then in this formula, you get, you see that anyway, so it was silly to turn it.
Yeah.
Yes. In the formula, E cube is roughly, if you forget about the constant, n to the 6. So if you divide it by n squared, it's n to the 4, right? You get that the crossing number is some other constant times n to the 4. Now, n to the 4 is the worst that you can get, because a graph can have n square edges at most. And even if every edge crosses every other edge, it is n to the 4. So this already shows that if you look at the complete graph, which is definitely dense in this sense, right? Then the crossing number of the complete graph will be some constant times n to the 4. So the challenge is to determine that constant. The other extreme, so what happens if the graph has few edges, of course, bigger than 4 times n, a linear number of edges. So this, I would say that this is sparse. So this is sparse, then E cube is n cube divided by n squared is n. Then you get that the crossing number of the graph is some other constant times n. So, and this is kind of obviously true, because assume that the graph has 3n minus 6, 3n minus 6 edges. Then there are no, maybe there are no crossings. Add another edge. If you add another edge, then there will be at least one crossing. So add 2 edges. Well, if you add 2 edges, then there will be at least one crossing. But if you delete that one, the one crossing involves 2 edges. So delete one of the edges. Then you have 3n minus 5 edges in which there is one crossing, and you remove one crossing, so there are at least 2 crossings. So whenever you add another edge, you add another crossing by induction, because there is at least one crossing. You delete one of the edges, with it you removed one of the crossings, and then you apply induction. So this means that there is a trivial bound that E for the crossing number which is at least E minus this 3n minus 6. So let's just write E minus 3n. This is a trivial lower bound. So if E is constant times n, then E minus 3n is also constant times n. So you kind of proved this thing, and the bound E cubed divided by n squared kind of connects these two extremes. And why is it tight? So it has to have E edges, the graph. So this means that the average degree is 2e divided by n. So you just divide the graph into disjoint groups of size 2e over n, then the number of edges will be right. And then in each part you connect everybody to everybody. And if you connect, if this graph you count the number of crossings apart from the constant, you will get E cubed divided by n squared. So it is, there are slightly better constructions, but as I said, now we are within a factor of 2 from the truth as far as this constant is concerned, and it may be interesting to try to determine that. Now here, let me stop for a second. So I will actually give very quickly, maybe this will be the only proof, a proof of this statement apart from the constant. It's very elegant, very short, so I recommend that you try to stay with me, although if you don't, then well, you just lose the fun because it's. But there is another proof, and this other proof, which I won't tell you, is not so elegant, but is more important for computer scientists, because the other proof is kind of a divide and conquer proof. It uses the separator theorem, various forms of the separator theorem. There is a separator theorem for planar graphs, which you may have learned in school, which says that if you have a planar graph, you can always delete roughly square root of n of the vertices so that the graph falls into two parts with no connection between them, which are of roughly the same size. And that's what computer scientists like, because this gives you the opportunity to divide and conquer, right? So if you can delete that, you compute something for one part, something for the other part, and you try to combine the two. That's the idea. Now, this other proof and the other approach that I'm not talking about was, it wasn't, maybe it was followed by Leighton, but why was Leighton interested in it? Leighton was actually interested, and that's what his PhD thesis is about representing graphs succinctly on a small grid. Today we would say that a small chip. And it turns out that if you have some kind of a network, graph, then the size of the smallest chip on which you can realize that network actually depends on the crossing number of the network. Now, at that time, it was not chips. It was very large-scale integration, VLSI design, and printed networks and things like that. But the idea and the mathematics are the same. Okay, so how do we prove this crossing lemma? So again, here is the crossing lemma, this E cubed divided by n squared. So for those who are online, doesn't have, but I just refer to it here so that whenever you are in doubt, then you can look at it. And so this is what we want to do, that the crossing number of the graph with E edges and then vertices, that means something. And as I said, the simple argument proves that the crossing number is at least E minus this, right? Just by induction. And the funny thing is that this is the only thing that we will be using. With one trick, which often raises its beautiful head in proofs in this area, we combine this with a probabilistic line. So we do the following. So here is our graph. Assume that we want to say something about the crossing number of the graph, and assume that we drew this graph is the smallest possible number of crossings. This is an optimal drawing, okay? And then we visit each vertex, and we pick each vertex, color each vertex red with probability P. It's the same probability independently from each other. So here I colored them. For me, it took a long time to do it, but I did it. As you see, I am not a high-tech person. So now we have these red vertices. And once we have the red vertices, we can look at the graph induced by them. So what does it mean? If you have an edge and both of the endpoints are red, then the whole edge we consider. So we pick the red vertices randomly, and then those edges in the graph that connected to red vertices, we call the red graph, and we denoted it by G prime. So look at this red graph. So what we do is that we just apply the simple lemma to the red graph, to G prime. Well, it's a random graph, so you may wonder that this is the rest of the proof, the whole proof. So you may wonder, I mean, we don't know what the red graph is, but there is something which is the red graph. It's, if you can call it a random variable. And since this inequality that the crossing number of G prime is bigger than E prime minus 3 times M prime, where E prime denotes the number of red edges, M prime denotes the number of red vertices. This is true no matter what red graph we get. It is also true in expectation. This is the same thing that if you have a function which is bigger than another function, then the integral of the function is bigger than the integral of the other function. And actually, we can tell exactly what these things are because so we had originally n vertices. So what will be the expected number? So this E means the expected number. What will be the expected number of red vertices? P times n. So this term becomes 3 times P. What will be the number of edges? We had originally E edges. The probability that an edge will be red means that we choose this vertex and this vertex, both of them will be colored red. The probability of that will be P squared. So the expected number will be P squared times E. Here, it's a little bit more complicated because if you have a crossing, then the probability that this crossing survives will be P to the 4. Will be P to the 4 for each of the crossings. So the expected number is P to the 4 times crossing number of G, except that maybe that the actual crossing number is even smaller than that, because maybe this red graph can be drawn better than what is the drawing inherited from the origin. For instance, this edge we could draw like this. But this only makes the inequality prove even better. And now after that, all you have to do is, this is true for every P. So you just set P like this, and you get this inequality, the constant. Okay. So this is what we have proved with a different constant. we refer to that as the crossing line, but it doesn't only have applications for chip design. It has many applications. It turned out to have applications in number theory, applications in combinatorial geometry, about the number of incidences between points and lines. So it turned out to be an extremely useful tool to know for problems that seemingly have nothing to do with crossing numbers. Now, if we assume something else about the graph, then we can have better crossing numbers. I don't want to say much about it, but in this, so just one example, for instance, if you assume that your graph does not contain K2 a cycle of length 4. That's a property of the graph. Then instead of E cubed divided by n squared, you get a better lower bound. And that's also tight. How do you know it's better? Because e to the 4 divided by n cubed is E cubed divided by n squared times E over n. And since E is bigger than n, I assume that E is at least 4n. It's indeed better. And in general, whenever you have a monotone property, which means basically that if it is true for the a graph, then it is also true for the subgraphs of the graph. Like this property, it doesn't contain a cycle of length 4, and of course, no subgraph of it contains a cycle of length 4. So for any such property, there is a better bound. Okay. Now, before we go further, I want to return this question about the straight line, non-straight line drawing. You remember that at the beginning I said that that in the most interesting questions it doesn't matter whether how we put the points, the actual, and how we connect them, whether by a straight line or by a Jordan curve. So clearly, we could modify the definition, and that's also a very valid question. Sometimes it comes up when you really insist on that you want a drawing in which the edges are straight line edges. And if you insist on that, then of course, the new crossing number, in the best drawing, you have at least as many crossings as if you didn't insist on anything, right? So this is a larger number. So the minimum number of crossings among those where you insist on straight line edges is at least this. And you may wonder whether how these two parameters are related to each other, and the answer is that they are really not. And this was discovered but actually it was discovered already earlier by Tarjan and Rosenstiel, but a really elegant example was found by Bielstock and Bean. So they came up with a graph whose normal crossing number is 4, but the other crossing number can be arbitrarily large. It's not, you cannot even bound it by a function of the smaller one. It can be as large as you wish. And let me just show you, because it's a beautiful construction. And in fact, I wondered at how everybody missed that for 10 years. Essentially, this is the construction. So this is a graph. As you see, there are these basic back vertices, and any two of them are connected by many paths of length 2. Yeah. These and these and these. And then to this graph, so and this m of course, this will be the one, the number of extra vertices here will be the parameter that goes to infinity. And then you add 4 other edges, these 4 other edges. Now, if you insist that all the edges are straight line edges, then by the fact you know that these edges should be straight line, this whole thing should be squashed into 0. This is not quite true because there are many ways how to draw this graph. In fact, you can redraw it so that this region here becomes the outer region. And then it's a different drawing, and maybe you can draw it in a better way. So for this reason, you take 2 copies of this graph next to each other, and it requires a little bit of thinking that here you cannot do anything clever. So if you draw it with straight line edges, then there must be one of these extra 4 edges, or in this picture, extra 8 edges, that should cut through one of these bundles and create a lot of crossings. You may wonder that okay, but who tells you that these bundles are drawn as bundles? No one tells you that. But you can assume it very easily, because take one of these paths and look at the other edges, that how many times they intersect. Look the other paths, again counting. So if for one of these paths of length 2, the number of crossings would be smaller than for the others, then I would just put all the others right next to it, and I would gain. So anyway, this is the whole construction, and you can describe the proof on half a page, but it's easier for you to check it if you have the time. So it's a nice. So this means, what is the moral of it? The moral is that the straight line crossing number is a completely different word. There are results about that, but I am not saying anything. Now, in the early literature of the crossing number, in every paper somehow, if you look back, it turned out that in every paper there was a different kind of crossing number used. And basically, there were 2 different things, except that the authors didn't realize it. So the first one is the one that I defined, that you just count the number of physical crossings, very natural. The other one is that you count the number of crossing pairs of edges. And you couldn't care less that whether 2 edges cross once or cross 100 times. Just one crossing pair. Maybe I wrote it for eternity now.
You could actually turn.
Oh, yeah, that's it. No, that doesn't matter. Doesn't matter. Just
yeah, it could help.
No, it's not important. You can also just follow my hand. So anyway, so these are these 2 numbers. So one is the pair crossing number. So the pair crossing number, here you count the number of crossing pairs. So if you count the number of crossing pairs, it can only be smaller than or equal to the number of physical crossings, because here in the original crossing number, you count if 2 edges cross 100 times, then you count it 100 times. Here you count it only once. So Géza and myself noticed this kind of strange thing in the literature in 2000, and we asked this question, which I think that is the most challenging question still in this area. So are these two crossing numbers the same for every graph? You would think that, okay, we can definitely try to find a counterexample by a computer, but life is not so easy because determining the crossing number and the pair crossing number, both of them are NP-complete problems. So actually for relatively small graphs, including like a complete graph is, I don't know, 15 vertices, it's a hopelessly difficult task to determine these numbers. And the main difficulty is that there are many different ways how you can draw a graph. It's not, although the number of vertices is small, the number of different ways how you can draw it is very, very large. Now, there is one argument which I would like to show you, if you can smoothly that everybody who looks at this problem in about 5 minutes comes back and says that no, this is complete nonsense. Actually, very clever people, good mathematicians, will come back several times because say, look, take the best drawing of a graph. Okay, so the best drawing of a graph, and look at two edges. If these two edges cross more than once, then what I do is the following. I just flip this. So if I look at this edge, then on this section, you know, this edge, I let this edge go like this. And on this section, this edge, I let this edge go like this. And then I got rid of two crossings, right? The number of crossings went down by 2, so it wasn't an optimal drawing. So this means that in an optimal drawing, two edges cross at most once. But if they cross at most once, then the whether or not we count the crossings with multiplicity or not makes no difference. So what's wrong with this argument? So I'm not telling you what's wrong with this argument. Actually, this is a correct argument, but it doesn't prove that the two things are equal. But you have to think about it a little bit. So it's a perfectly correct argument, but it doesn't prove that the two things are equal. Okay, you can sort of meditate on that if you are interested in this question. So, okay, we don't know what. Let me look at the time because I definitely don't want to.
5 minutes.
Okay. Since we don't know if they are equal, and we know that the pair crossing number is smaller than the crossing number, we actually want to say that the situation is not that bad as it was in the case of the rectilinear crossing number and the crossing number. So you can at least bound the larger one, the crossing number, in terms of the smaller one. And I mean, I would be very happy if we could prove that the crossing number of a graph is at most n equals 10 to the times the pair crossing. But we are far from knowing that. In fact, this would be my conjecture, that not with 10 to the 10, but with a small constant, like the crossing number is never, so there may be a slight difference, like maybe twice as big as the pair crossing number, but not more. That would be my conjecture. But what do we know now? what we know is, so the best result that we know is due to, again, a PhD student, Mexican PhD student at MIT, Sole P, I guess, and not Pi, who proved that the crossing number is bounded from above by constant times the pair crossing number to the 3/2. And what I will indicate, so there were a series of results, but the first one was just that the crossing number is bounded by the square of the pair crossing number. And that I can indicate, and I will indicate, and this will be the last thing that I show to you. And I show to you because it has it gives me the opportunity to tell you the Hanani-Tat theorem, which is a beautiful theorem and a very useful one. And few people outside the graph drawing community know that. So Hanani, under the name of Chojnacki, published it in 1934 in Poland and in German. Tat didn't know that. He rediscovered it in 1970. So what is the theorem? The theorem says, very remarkable theorem, that assume that you can draw a graph in the plane, also true in other surfaces, so that any two edges cross an even number of times. Then you can also draw it in such a way that any two edges cross a zero number of times. Zero is an even number. So if you draw it somehow that any two edges cross an even number of times, then the graph is planar. And for many, many years, there was no better proof of this theorem just by characterizing graphs that can be drawn so that any two edges cross an even number of times. And it turned out to be the same as the Kuratowski theorem characterization of planar graphs. So that was the proof. Now we have better proofs of that. And so Géza, Tóth, and I managed to generalize this theorem. It's an unpleasant proof, but the statement is not so unpleasant. So take any graph, G, which is drawn in the plane, and look at those edges that cross every other edge an even number of times. So for instance, if there is in the drawing an edge which doesn't cross anyone else, then that's fine, because it crosses every other edge 0 times, which is an even. Then I can redraw this graph in such a way that these edges don't participate in any crossing. So what's the relationship? In the Hanani-Tat theorem, every edge crosses every other edge an even number of times. Then you can redraw it so that no edge participates in any crossing, so all the edges, so this is a planar drawing, right? You look puzzled. So I look at any drawing of a graph, look at those edges that cross everybody else an even number of times. I color them red. By Tat theorem, the red graph is a planar graph, can be redrawn without any crossing, but I can redraw the whole graph in such a way that those red edges don't cross anything else. And that shows, I just copied this theorem here. This has the corollary that the crossing number is twice the pair crossing number. Why? Because I look at the graph, I redraw it in such a way as I said, so that those red edges, these are the red edges, they don't participate in any crossing. These are those edges that are non-red. All the other edges, they are non-red, even if every other edge crosses every other edge. The number of crossings is this big. But the number of other edges is at most 2 times the pair crossing number, because in the worst case, every crossing where two edges cross each other uses up 2 of these other edges. And this is I think that this is a good point to stop. And thank you very much for your attention.
Thank you, Janos. Yes. So let me stop on the recording as well. And